in this example, let's evaluate the integral over c of y minus x dx plus 2x minus y dy, where c is equal to c1 union c2. It's the boundary of, all right, c1 is this outer rectangle here. c2 is this inner, it's a square here. And R is the region inside the big rectangle but outside the square. Okay, so R, in other words, is highlighted with these green diagonals. Huh? No, I'm saying this is the boundary. This is the boundary of, and I'm telling you what the region is with a picture.
Y-axis, or is it?
No, C1 is the entire curve, the entire rectangle with, so it's not a smooth curve, but it is piecewise smooth. So each one of these pieces together is C1. Each side, this side, this side, this side, this side, that is C1. I think one of the dashes got erased. Okay. So let me be specific here. This goes out to 5, and this goes out to -5. And I think when I was cleaning this up, I might have just accidentally erased it. So 1, 2, 3, 4. So I think I just accidentally erased that scale mark. Thank you for pointing that out. Everybody good? And then it goes to a height of 3 and down to -3. Okay? Well, there's a hole in that region. It's not simply connected. But there's a trick we can do here to make it at least fool the integral so that Green's theorem works. It's kind of neat. What we can do is we can add in 2 more curves, actually they're line segments, such that when you integrate, they'll cancel out on each other. The line integral part would cancel out if we were actually evaluating the line integral. So let me go through the process and explain. Now, what I'm about to draw is actually going to be part of the x-axis, but I'm going to draw it off the x-axis because there's going to be 2 of them, and you wouldn't be able to distinguish between them if I drew them both on the x-axis. So I'm going to draw this guy slightly below the x-axis, but it's actually supposed to be on the x-axis. I know, confusing, but it would be more confusing the other way. And so this is another curve. It's a straight curve, and it's oriented like that, and I'm going to call that C. I'll call it C3. So is that showing up, or do I need to use a different color? Yeah, I think it shows up. Okay. And then C4 is also on the x-axis, but I'm going to draw it a little bit above the x-axis so you can see it. So C4, I'll do in purple here, is going to be the exact same line segment, except it's going to be oriented the other way, this way. C4. Okay? So that my claim is that as far as evaluating the integrals, it doesn't matter if we integrate over this guy or if we consider C the union of all 4 curves. So C1 union C2 union C3 union C4. Now, let me give you a justification for this. So we're gonna take C to be this. We're gonna change it to this. Take C to be this. If I integrate over this version of what I'm calling C, now I'm gonna do something here that you're only allowed to do if you get a bachelor's degree or better in math. I'm gonna leave off notation. I know. I'm going to write it without, so this is, okay, the first one I'll write it with. So this is, I'm representing the line integral here. I'm not using a double integral yet. So that's what I want to find. And my claim is that this is equal to the line integral, so I'll leave off notation in the next step, over C, where C is just the union of C1 and C2. So why would that be true? Let's split up. Remember, integrals are additive over those line segments. The integral is additive. So let's split this integral up. So my claim is that that guy is equal to Now this is where I'm going to leave off the notation, but again, please don't do this on the test because I don't know if you know what you're doing when you leave off notation. That's the issue. It's a serious issue. But for teaching purposes, this will speed things along. C1, this integral up here, is going to be the integral over C1 plus the integral over C2 plus the integral over C3 plus the integral over C4. It needs a C. Just 4. The integral over 4. What does that mean? Okay. Now, would you buy this? I'm just going to recopy the first 3. I could consider C4 notationally, we discussed it the other day. It has the opposite orientation of C3, right? So the line in purple has the opposite orientation of the line in yellow. So I could replace C4 with negative C3. And what can I do with that negative essentially? Pull it out front. Remember that? We talked about that the other day. So that this guy then would equal the integral over C1 plus the integral over C2 plus the integral over C3 minus the integral over C3. What happens? They're gone. And so we just get the integral over C1 plus the integral over C2, which is exactly what this guy would split up to be. Furthermore, I claim that this orientation is positive because, we have to satisfy the hypotheses of Green's theorem to use Green's theorem. Now, you could argue, look at C2. It appears to be oriented clockwise, right? But you'll learn very soon that, as I've already said, that idea of clockwise orientation has some limitations, and we've come up against one. Really, what you want to think of it, like this. Suppose you have an ant crawling on the screen, not on the other side of the screen, but this side of the screen. And I'll use my highlighter here. And so the ant it doesn't matter where it starts. Say it starts here, and it crawls along following what we described as the positive orientation, right? Really what has to be true for it to be positive orientation is that region R in green has to be on the ant's left side for it to be a positive orientation. So check out what happens. The ant's cruising along. Oops, I shouldn't have chose yellow. Cruising along, and then it goes in. Now this is along the x-axis really, right? Goes on C3, and then it has to go this way. But look, the region is still on its left. And that's really how we think of it, how we think of a positive orientation. And then we go back out along the x-axis. The whole time, the region is on its left, the ant's left side from the ant's perspective. And I can draw it without lifting my pen, my stylus. So it's going to satisfy the fact that we need it to have positive orientation, and you have to actually be able to draw the curve without lifting your pencil for Green's theorem to work also. All right. So long story short, Green's theorem applies. So let's use Green's theorem. All right, so let me back off the view here so we can hopefully keep most of this in view. So Green's theorem, so that was just to convince you that it should work. Remember what Green's theorem says. Green's theorem says that the line integral f dot dr under the right conditions is equal to the double integral over r. That's got to be the region that C encloses, and it does. The way you can draw it without lifting your pen, the region is on the left. C does enclose it in a kind of a weird way. Of dq dx minus dp dy. dA. So what does this tell us to do? Find those partials. So what's P? P is that guy, Q is that guy. So let's see if we can set up the integral and do everything at once here. So the line integral then, f dot dr, is going to be equal to the double integral over, I'm going to leave it r. What's dq dx?
Negative x, or
So here's q, 2x minus y. What's derivative with respect to x? 2. There you go. With respect to just x, dq dx. Okay, what's the derivative of, so we're going to subtract off the derivative of p with respect to y? Just 1, right? Just subtracting off 1. dA. So what's the integral? 1. Well, that's a special integral, right? So what does this integral represent? The area of the region R. The good news, the region was formed using rectangles, right? So we don't have to use calculus. We don't have to evaluate this integral. So you're going to find the area of the big rectangle with the hole in it. So this is a hole, right? You got to take that hole out. Okay, so what's that going to be? That's going to be, what are the dimensions of the big rectangle?
10 by 6.
Yeah, it's 10, right? It goes from negative 5 to 5. So 10 goes from negative 3 to 3 on the y-axis, negative 5 to 5 on the x-axis. So the horizontal dimension would be 10, the vertical dimension 6. And then this square actually went from negative 1 to 1 on both axes. So 2 by 2. And we're subtracting that out. Do you buy that? So 60 minus 4, 56. Now, it is in area square units, but we actually evaluated a line integral, and that may represent something else. So I'm going to leave off units, right? Okay? I like that example.